All right, Algebra 2 in 13.8, which I believe in this textbook is the last section in Chapter 8, we get into something a little bit weird called the reciprocal trigonometric functions. So you guys have learned for a couple of years now, going back to geometry last year, and then earlier in this chapter, the three what we'd call basic trigonometric ratios here of sine, cosine, and tangent. Well, there are three more out there that we haven't taught you guys yet that have some nice applications when you get into higher level math and science, and we're going to learn those today. And those three I'm going to write out for you in just a second, but let's take just a moment before we get to that and talk about how we define sine and cosine and tangent on the unit circle. So I've got this diagram over here on the right, our wheel diagram of the unit circle, and any point on the unit circle, I've got this one right here in red, but it could be a point located right here, or right here, or right here. It doesn't have to be one of the special angles. Any single point that's on that unit circle can have its coordinates expressed by the ordered pair x, comma, y. X, of course, being your x coordinate and y being your y coordinate. And then I've gone ahead in blue here and already drawn in what we typically draw from any point there, a radius that goes back to the center of the circle here, and then an altitude that goes straight down from your point, always creating a right angle, guys, with the x-axis. You never, never, never want to draw this thing over here to the y-axis. That is not how we do it. Now, if this ordered pair is x comma y, think about that, guys. That explains how you get from the origin to this point right over here. And an ordered pair means that you travel this far to the right. So this coordinate on that triangle right there is always going to be the x-coordinate of whatever point that is. And then, once you move to the right in this case, you're then going to move up whatever this distance is. So y is the length of the other leg on that triangle right there. And, as we've been talking about most of the chapter right here, the hypotenuse is called r. That's going to be the radius of your circle right there, and also the length of the hypotenuse of the triangle. So you have a right triangle here whose side lengths, the legs, are x and y, and the hypotenuse is going to be r. And of course, because it's a right triangle, the Pythagorean theorem governs that relationship between the three sides. X squared plus y squared always has to equal r squared. Now that's true if you're on a unit circle whose radius is equal to 1, but it's also true if you're on a non-unit circle, if it was much bigger than that, which will happen a little bit later on in this section. So, with that in mind, guys, theta is this angle right here in standard position between the positive x-axis and then the terminal side. And so the sine of theta, if we think about sine and cosine and tangent in terms of SOHCAHTOA from a triangle, sine is opposite leg over hypotenuse. So from theta, your opposite leg over here is y, and your hypotenuse is r. Now, depending on what teacher you have for Algebra 2, you may have seen these definitions earlier on in the chapter or not. A lot of people still cling to the old idea right here that sine is equal to the opposite leg in a triangle divided by the hypotenuse, and that idea is certainly not wrong. The only problem is it doesn't really help you when you're dealing with an angle like pi here, because there is no triangle, okay? Your height of that point there is 0, and so there is no opposite leg and there is no hypotenuse. So these XYR definitions kind of help you with those quadrantal angles. Okay, back to it, guys. Cosine is adjacent leg over hypotenuse, which in this diagram is going to be x over r. And then tangent is opposite leg divided by adjacent leg, and that is going to be y over x. Okay, so those are the three, what I would call the XYR definitions of sine, cosine, and tangent. Now, we've got some new vocab right here, and I realize now as soon as I saw this, I should have written these words out at least once the first time around. CSC, everybody, is an abbreviation for what we call cosecant. All right, that'll probably be the one and only time you ever see it written all the way out. SEC then is secant, not the Southeastern Conference, and COT is not a cot that you sleep on, but that right there, guys, is called cotangent. cotangent of an angle. So as I said, those are probably the only 3 times you'll ever see those ones written out. Now, if you panic just a little bit when you thought, wow, it's taken me a long time just to understand sine, cosine, and tangent, and now you're throwing 3 new ones at me, well, relax. These are called the reciprocal trig functions because each of these 3 is simply the reciprocal of one of the other ones here. For example, sine of theta, we just said, was y over r. Cosecant is the reciprocal of sine. That is going to be r over y. Nice and easy. Cosine we defined as x over r. Secant is the reciprocal of cosine, which is going to be r over x. And as you could probably guess from here, since tangent of theta is y over x, cotangent of theta is that reciprocal, which is going to be x over y. I probably should have left myself a little bit more room and written this down here too, and if you have the space, maybe just do this right after each one of those 3 definitions here, guys. Actually, you know what? If I were a smarter guy, I would do something like... Let's see if I can move all of this down and out of the way. Well, okay, yeah, we probably got what we needed out of there. Okay, probably another definition that I should have written down here is what we said but didn't write. Cosecant of theta is simply the reciprocal, or 1 over the sine of theta. Secant of theta is the reciprocal of cosine of theta, and then cotangent of theta would just be 1 over the tangent of theta. So both of these columns right here, this one in blue and this one here in purple, those are good definitions to know for cosecant, secant, and cotangent. All right, probably don't need to panic too much about this section, guys. It's really not that bad. I'm going to have you do 2 types of problems right here, but it's not a very long section. First of all, you guys all know, and you've been doing it since geometry last year, how to find sine and cosine and tangent on your calculator. You can use your calculator to find the reciprocal trig ratios. So we're going to do 1 cosecant problem, 1 secant problem, and 1 cotangent problem. But if you start looking at your calculator for these buttons, you're going to be disappointed. You're not going to find them. Most calculators out there do not have buttons for cosecant, secant, and cotangent. So how are we supposed to do that? Well, let me go back, everybody, to these definitions right here in blue. And the first problem I was about to ask you is, what is the cosecant of 71 degrees? Well, right here we wrote down that cosecant of theta is, let's pay attention to this definition right over here, 1 divided by the sine of theta. And whatever this theta is, this theta needs to be the same angle. So you can find cosecant on your calculator by simply taking the reciprocal, or 1 over the sine of 71 degrees, because cosecant and sine are reciprocal trigonometric ratios. Now, I wish I could show you guys this on a TI-84, but there is no app on my iPad for that. But if you're opening up your calculator, what I want you guys to notice is probably at this point in the chapter, near the top right, in that little status bar up on top, it's kind of in gray with white typing there, font there, you guys should have the word degree written. And since we're talking about 71 degrees, you want to make sure that your calculator is in degree mode. Now I'm going to go to my TI Inspire Cast, which I use for calculators here. And in the top left-hand corner of my screen, a little bit down, you guys might see an RAD that I have right there. My calculator is in radians. So what I need to do is go to settings right here, and my second one down is radians, and I'm going to change that to degrees, and then go back and then hit done, and now I've got a DEG on the top. For you guys, if for some reason your calculator is in radians, you're going to hit the mode button, which is right next to second. All right, you're going to hit the down arrow twice. You're going to hit the right arrow once so that it's blinking on degree. Hit enter, so you're in degrees now, and then hit second, quit, and that'll take you back to this main screen. And now I'll type this in just the way that you guys can do the same. There's really no need to do a fraction right here. I'm just going to type in 1 divided by, and then we had the sine of 71 degrees. Okay, and at that point, if I hit L, my Smart Aleck calculator gives me that. So here you go. This is probably what you guys got here, 1.0576, blah, blah, blah. Directions, guys, for most of our worksheets and tests is to round to the nearest 10,000th. That's 4 decimal places. So 1.0576 is what we're going to write here. 1.0576. That's it. That's how you do problems like this. So, secant of 254 degrees, secant is the reciprocal of cosine. So that's 1 over the cosine of 254 degrees. And let's see what we get there, guys. So 1 divided by cosine of 254, and I'll try to be smart about this one that time. There you go. And I got this number right here. Did I do that right? Yeah, 254. So our number here is negative 3.62, 79, and then with a 5 after that, we would round the 9 up. I would think of it as rounding up the 79, which becomes an 80. So negative 3.6280. 6280. And guys, you do need to include that 0 as the fourth digit right there. Otherwise, if you just write negative 3.628, now that looks like you only rounded to 3 decimal places instead of 4. So make sure you put that 0 at the end right there. And the last one I've got for you, I think I remember what I did when I wrote this, should be interesting. Cotangent of 900 degrees is going to be 1 divided by, and cotangent is the reciprocal of tangent. That one's pretty easy to remember in terms of the name. And let's see what happens, guys, when we type in 1 divided by the tangent of 900 degrees. Survey says, all right, guys, your calculator, in fact, I'm going to do this. Sorry, I know you guys can't see me typing this right here, but I'll type really loud so you can hear me. 1 divided by the tangent of 900 on the TI-84 gets me an error message, and it says divide by 0. Now, what that actually means, guys, is that the denominator of this thing, tangent of 900 degrees, is 0. And if I think about that, give me just a second, guys. Here's my unit circle. One complete circle is 360 degrees. Another complete circle is 720, and 720 to 900 is another 180 degrees. So I'm talking about this angle right over here, which is the ordered pair -1, 0. All right. And since tangent, let's write this out here, guys. Tangent of theta is defined, we said on the last page, as y over x. That right here would be my y-coordinate, 0, divided by my x-coordinate, which is -1. And as we've said many, many, many times this year and over the past several years, 0 divided by any other number, anything other than 0, is 0. However, the cotangent, then, of theta is going to be the reciprocal of that, x over y. Now, using the same values, my x-coordinate is -1, and my y-coordinate here is 0. Well, guys, anything divided by 0 is going to be undefined, and that would be our answer then right here. So one of the things you're going to have to watch out for here, unlike sine and cosine, which have a domain of all real numbers, and that means no matter what you type in for sine or cosine of an angle, you will always get a real number for your answer. The other reciprocal trig ratios, actually, and tangent as well, tangent, cosecant, secant, and cotangent, you will occasionally get an undefined answer in a problem such as this. All right, guys, so that's how you use your calculator to find these reciprocal trigonometric functions. Now, that's, let's be honest, not super hard. You're just typing that in, albeit with the division right there. But now, let's get back to the type of problem that we saw earlier in this chapter and that I promise you are going to see on your test at the end of this chapter. Find the exact value for each trig ratio. And I probably should have put in the directions right here, guys. This is a non-calculator question. Now, when we say exact value, we are not looking for decimals here. We are looking for something that is exact, meaning a fraction, and it might even have radicals in there, which we saw a lot from earlier on in this chapter. So let's dive into this one, guys. The cosecant of 5 pi over 4. Okay, just in case we forgot, I know every Algebra 2 teacher explains this a little bit differently, but here's how I like to think about things. All right, guys, I've got my x-axis and my y-axis, and here's my unit circle. Not terribly well drawn, but that's okay. We got to find where 5 pi over 4 is before we do anything else. And if you happen to have this memorized, good for you. If not, let's just review a couple of tricks right here. Forget the 5 for a minute. Pi over 4 is an equivalency I'm hoping you guys have memorized. That's 45 degrees. We're going to go around this circle, starting from right here, of course, in 45-degree steps. And how many of them are we going to take? 5 of them. That's what the numerator tells us. So we're going to take 5 steps of 45 degrees each. So right here, guys, would be 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and right here, everybody, would be 5 pi over 4. So let me switch colors to purple right here. This is the angle that we're talking about right there, guys. That angle from here to here is 5 pi over 4. And what I like to do then is find this point right over here and draw my altitude always back to the x-axis, and there we've created a right triangle. And what I'm hoping you guys remember is what our reference angle right here is 45 degrees. This is a 45, 45, 90 right triangle. So, what I asked my students to memorize earlier on in this chapter are the 3 side lengths for a 45, 45, 90 right triangle if you're on a unit circle. So I would always make my radius 1, and in that case, both of the legs then were the square root of 2 over 2. So root 2 over 2. I, of course, have also seen it done by some teachers out there where what they will do is they will say, okay, each of the legs is 1 and 1, and the radius is the square root of 2. So both of those are correct. Either one will work for you right here. This method here that I usually use works better, I think, just my opinion, for sine and cosine. Actually, this one right here probably works better for what we're doing here in cosecant. But you know what? I'll leave them both there. They're both going to get us the right answer. Now, we need the cosecant of this angle right here. Now, cosecant, let's remember, is the reciprocal of your sine ratio. And as we wrote a few pages ago, the sine of theta is defined as y over r. Well, that means that the cosecant of theta is the reciprocal of that, which is r over y. So looking at my diagram right here, my radius then, the r that I need on top, is going to be 1. And then the y-coordinate is this piece right over here. Now, I just realized I meant to come back and do something, and I didn't. We're in the 3rd quadrant right here, guys, where both your x-coordinate and your y-coordinate would both have to be negative. So on the diagram on the bottom, those 1s would both be negative as well. So back to where I was, guys. Cosecant is r over y, my radius is 1, and my y-coordinate here is negative root 2 over 2. Ugh. And that's kind of ugly here, guys. So let's talk about a way that we can clean that up a little bit. We're going to take our numerator, which is 1, and rather than dividing by a fraction, we're going to multiply it by its reciprocal. Okay, so this becomes multiplication now by 2 over the square root of 2. And you can put the negative wherever you want there. Most people like to leave it up on the top. Now, more trouble. You can't leave the radical in the denominator, so we would need to multiply by the square root of 2 over the square root of 2. Okay, and what's that going to do for us? The numerator, you can kind of forget the 1, guys, is negative 2 multiplied by the square root of 2. Can't do anything with that. Our denominator is root 2 times root 2, which equals 2. And now something cool happens. The 2's cancel each other out. So our final answer here, guys, is going to be negative square root of 2, and that's what we've got here for the cosecant of 5 pi over 4. Now let me look at the exact same problem again, but let's focus on this second circle right here, which I know some teachers like to teach those values right there. In that case right there, if we remembered that cosecant of let's write all that out, 5 pi over 4 was equal to, and again now I erased it a second ago, sine would be y over r, cosecant would be r over y, there you go. Here, the radius would be the square root of 2, and the y-coordinate would be negative 1. Oh, and like I said, this diagram is actually a lot easier for what we're doing right now because anything divided by 1 is just that number itself. Anything divided by negative 1 is its opposite, negative square root of 2. So, pretty clearly, using this diagram right here was easier on this problem than the unit circle diagram that I usually tend to use. But either way, you will get the same answer, and it's correct. All right, let's do another one here, guys. Secant of 11 pi over 6. All right, so let me draw. That was a little better diagram right there. Okay, I like it. That's where we're at right now. Where in the world is pi over 6? Or excuse me, 11 pi over 6. Let's ignore the 11, and our step size is here, guys, pi over 6, hopefully we have this memorized now, is 30 degrees. And we're going to take 11 of those 30-degree steps going around the circle. So starting right here, we're at 1 pi over 6, 2 pi over 6, 3, 4, 5, 6, 7, 8, 9, 10, and there's 11 right there, guys. So 11 pi over 6 is going to get us to this point. Let me go ahead now. I'm going to switch back to blue. And let's draw our triangle right there. Okay, it looks like that, and it looks like that, and there's your right angle. So hopefully you guys recognize what kind of triangle that is. This is a 30, 60, 90 there. And the way that I would label that triangle is to put 1 for the hypotenuse there, 1/2 for the short leg, and then the square root of 3 over 2 for the long leg. The 1/2 should be negative now because we're going below the x-axis, but the root 3 over 2 should stay positive. So at that point, if you wanted to list everything out here, my x-coordinate is root 3 over 2, my y-coordinate is negative 1/2, and the radius on my unit circle is going to be 1. All right, again, guys, the secant of 11 pi over 6 is the reciprocal of cosine. And as we said earlier, cosine of an angle is always going to be x over r. Secant, then, let's write that one out, I guess, too. Secant is the reciprocal of that. That'll be r over x. So your radius here is going to be 1, and your x-coordinate, we said, is root 3 over 2. Now, again, we don't want to leave this as a complex fraction, so this is going to be your numerator, 1, multiplied by the reciprocal of your denominator, which is 2 over the square root of 3. And once again, we have a radical in the denominator. We've got to clean that up. We've got to multiply by root 3 over root 3. So my numerator, 1 times 2 times root 3, is just 2 root 3. And our denominator, root 3 times root 3, is just 3. Nothing cancels right here, guys. So that's our answer for the secant of 11 pi over 6. All right. Hopefully we're kind of looking at that and saying, okay, that's not too terrible. Let's take a look at this one right here. Cotangent of negative 11 pi over 3. So threw a couple of wrinkles at you right here. For the first time, we're going with a negative angle, and 11 over 3 is pretty big. You might know already where I'm going with this one, but let's see what we've got. All right, guys, so here's our setup here, and here, I'll make that a little bit bigger, is our unit circle. Let's talk about where negative 11 pi over 3 is. Again, ignore your numerator for right now. Pi over 3, I'm hoping we know, is 60 degrees. So we're going to go around this circle in 60-degree steps, and we're going to take 11 of those steps, but because the angle is negative, we're actually moving clockwise now, guys, the opposite direction of where we normally go. Okay, 60-degree steps, everybody, starting right here. Here we go. That is 1, 2, 3, got it, 4, 5, and 6. Still got a long way to go. 7, 8, 9, 10, and 11. Okay, so negative 11 pi over 3 gets us into the first quadrant. I didn't realize that one right there. Okay, into the first quadrant. So there's my radius, there's my altitude, and there's the right angle that we have right there. Okay, gotcha. 60-degree reference angle right here. So the way that I would label this is 1 for my radius, 1/2 for my short leg, and root 3 over 2 for my long leg. Since we're in the first quadrant right here, everything is going to be positive. Now, cotangent is the reciprocal of tangent, and our XYR definition for tangent is y over x. That means, guys, that cotangent of theta is going to be the reciprocal of that, x over y. So on this diagram here, guys, our x-coordinate is equal to, this is going to be ugly, 1/2, and then it divides by our y-coordinate here, which is going to be the square root of 3 over 2. Nobody likes complex fractions, and we can't leave our answer in that form. So what do? We take our numerator and leave it alone, 1/2, but then multiply by the reciprocal of the denominator, which is 2 over the square root of 3. All right, the 2's cancel. That's nice. And that just leaves you with 1 over root 3. But again, we will multiply here by the square root of 3 over the square root of 3. And I think this is going to give us our final answer now. The numerator is just 1 times the square root of 3, which is root 3. And the denominator then is root 3 times root 3, which is 3. And that's what we came up with right here for the cotangent of negative 11 pi over 3. Now, guys, that was everything that I had for you right here. I am going to go ahead. I realize now I probably should have added one right here. I'm going to throw one more problem at you right here. And the reason why is because I was looking at your homework right there, and I think there's a problem like this that's on there. So what we're going to do, guys, is we are going to find, and I'm going to go back and I'm going to do cosecant again. Find cosecant of theta if. Now this time I'm not actually going to give you guys what the angle is, but what I'm going to do is tell you the coordinates of a point that are located on the terminal side of your angle. Let me show you what that means. So find cosecant of theta. If the ordered pair, and what do I want to do with you guys here? We're going to go with the ordered pair of, let me think. Okay, we are going to go with a negative 7 right there, and then we're going to go with let's go with a negative 24. Okay, if that ordered pair is on the terminal side of theta. Okay, gotcha. So, unlike the last few problems, it's not like you guys can just kind of sketch this out and think about your unit circle diagram and run with it, but in a way, this does kind of work. We're going to try to plot this point right here of negative 7 and then negative 24. So from the origin, we're going to go 7 units left and 24 units down. Now, 24 is a lot bigger than 7, so I'm guessing that point might be located roughly right about here. Let me label that. Negative 7, negative 24. We're definitely in the third quadrant. Now, just like always, I'm going to switch to blue here. Just like always, we draw our radius right here, and we draw an altitude always back to the x-axis, and here's your right angle. Now, we already know the coordinates of 2 of the sides of this right triangle. The horizontal component is x, that's negative 7, and the vertical component is y, that's negative 24. What I'm hoping is obvious to you guys here, though, is that this diagram does not represent a unit circle, because in a unit circle, the radius has to equal 1. Well, this hopefully doesn't make sense to anybody here. The hypotenuse of a right triangle has to be the longest side, and there's no way that 1 is longer than 7 or 24, ignoring the negatives. So in a problem like this, guys, we're going to have to find the radius. And to do that, I'm going to go back to a simple little idea that we had a long time ago, that I moved, and it's right there. No matter where you are on the unit circle, guys, you always have a right triangle formed by x and y for your legs and r for your hypotenuse. And that means that the Pythagorean theorem will tie together all 3 of those sides. So I'm going to do leg squared, and really that negative is in parentheses here, plus the other leg, negative 24 squared, is equal to my radius, or my hypotenuse, squared. So go ahead and do the math on this. Really, the negatives are just going to go away here, everybody, because when you square a negative, it becomes positive. And we're going to get a 49 plus, oh boy, I'm pretty sure that is 576 is equal to r squared. Adding those two together, I believe we're going to get 625 is equal to r squared. And then we'll take the square root of both sides. And because I gave you guys some nice numbers here, I don't know if anybody noticed it, we ended up with a whole number here for r, 25. This is a Pythagorean triple, everybody, 7, 24, and 25. So what that means right now, guys, is we know everything we need to know. At this point, our x-coordinate that was given to us is negative 7. Our y-coordinate was given to us as well. That's negative 24, and we just did the work to find r, which is 25. So if I asked you guys for the cosecant of theta, the XYR definition of cosecant, well, that is the reciprocal of sine. Sine is y over r, so cosecant becomes r over y. Our radius here is 25, and our y coordinate is negative 24. And good news, everybody, you can't do anything to simplify that. Now, I never like my negatives on the bottom of my fraction, so I'll just move it out to the front here and make it negative 25 over 24. Or, of course, you could put it in the numerator and make it negative 25 over 24. Any of those three formats would be fine. I think that one's probably the best. And that's how we would handle a problem like that, where they give you a point on the terminal side of your angle. So they never actually told you what this angle theta was right here, but that's okay. You really don't need to know it. By giving two coordinates here, we were able to come up with a third, and once you know x and y and r, you can find any of the 6 trigonometric ratios without too much trouble. Okay, guys, that is everything I have for you right here from section 13.8. Hopefully that makes some sense. So let's give that homework a try and let us know when you guys have questions. Good luck, everybody.